So let's remember, let's start by remembering what we did last time. The last topic that we covered last time was derived distributions. So we are specified a random variable x, and somebody defines another random variable y as a function of x. The question is determining the probability distribution of this new random variable y. Here's an example, the second example for this. We solved one example last time. Okay, this example is concerned with finding the PDF of y, which is x squared. Okay, in terms of the PDF of the random variable x, which has a PDF, fx of x. Okay, so what do? Do you remember the standard procedure that we defined last time? It's pretty straightforward. In order to go to the PDF, we pass through the cumulative distribution function, the CDF of y. What is the CDF? The CDF, big Fy of y, is the probability that y takes values less than or equal to some value lowercase y. Okay, this is a probability. We all know how to compute this. But we need to compute this using the PDF of x. Okay, so let's see. Now in this example, y is nothing but x squared. Okay, so put here x squared less than or equal to y. This event is true whenever y is positive and the absolute value of x is less than the square root of y. In other words, it's true whenever x is between negative square root of y and the positive square root of y, as long as, of course, y is positive. And it's 0 otherwise. This probability is 0 otherwise. Does everybody see this? So if you give me a value of y, if that value of y is positive, then I can compute this probability as this event is equal to this event. Okay? If the value of y is negative, this probability is 0 anyway. Okay, so now, what is this? This is simply fx of square root of y minus fx of negative square root of y. Right? Using the definition of the cumulative distribution function. Why? Because this is the difference of the events, of the probabilities of the events. X is less than or equal to square root of y, and x is less than negative square root of y. But since x is continuous, I can replace less than square root of y, negative square root of y, by less than or equal to negative square root of y. Hence, I get this. Any problem here? Alternatively, we could have written, let me just say here, or we could have written this probability as the integral from negative square root of y to the positive square root of y. What? Fx of x dx, provided y is positive and 0 otherwise. Any problems? Now there's only one remaining step, which is going from the CDF of y to the PDF of y. How do we go from a CDF to a PDF in the case of a continuous random variable? In the case of a continuous random variable, the PDF is the derivative of the CDF, right? By definition. In fact, by definition of the CDF, right? Hence, we basically have to differentiate this expression or this expression, whichever you feel like doing. Let me go by this. What is the derivative of the first term? The derivative of fx is small f of x, right? Because the derivative of, let me write here what I mean. D by dy, we're talking about d by dy, or dy, fx of square root of y minus fx of negative square root of y. Okay? This is when y is positive and we have 0 otherwise. Right, so I need to differentiate this expression. What is that? Let me draw a line here. Derivative of the first term is nothing but fx of square root of y, but I also need the derivative of the argument of the function. What is the derivative of square root of y? 1 over 2 square root y, right? Any problems? And the second term, here I have a negative coming from here and another negative sign here. They make each other positive. Fx of negative square root of y times 1 over 2 square root of y. Okay. In other words, we have 1 over 2 square root of y, fx of square root of y, plus fx of negative square root of y, whenever y is positive and 0 otherwise. And that is the PDF of the derived random variable y. So let's go over the procedure once more. We start by forming the CDF of the new random variable, the CDF of the derived distribution. It's nothing but a probability. We express this probability using the functional relationship between x and y in terms of x. And now we compute this probability because we know everything about x. Once we compute this probability, if y is not continuous, we would have to stop here. If y is continuous, we can differentiate this to get the density function of y. You just have to be careful about the regions in which the density function is valid. Okay. Any questions about this? Let's look at another example. Today is all about examples. So I'm going to erase this part. Here's the second example. This example gives us a general rule about a linear transformation done to a random variable. Show that if y is ax plus b, where a and b are constants, where x has PDF fx of x, and a is different from 0, a and b are scalars, that the following is true. Fy of y is 1 over the absolute value of a times fx evaluated at y minus b over a. Okay? So there's a special case where whenever a is -1 and b is 0, the density function of negative x is the density function of x flipped around the origin, fx of negative x, which sort of makes sense. let's first start thinking about this. You have a random variable x, say it's uniform between 0 and 1, and I'm thinking about negative x. Negative x will be between negative 1 and 0. And it only makes sense since I'm getting every value of negative x by inverting the corresponding value of x. It only makes sense that the density of the new random variable negative x at a certain value is equal to the original density at the negative of that value. So that makes sense. That's not a big, big leap. Now, if you look at this, this also sort of makes sense. Y takes on the value script y or small y. What is the sort of the event that y takes the value small y? Well, it corresponds to ax plus b being equal to small y. So that sort of means x is y minus b over a. Okay? Except we have this scaling coming up. The scaling by 1 over absolute value of a. And you can guess that that has to do somehow with normalization. So let's derive this and see whether we get the same thing and whether we understand the intuition for this scaling. Okay? So how do we begin? Remember our general procedure for this. Y is a function of x. I want to find the PDF of y. So first find the CDF of y. That's the general procedure. So let's find the CDF fy of y. That's the probability that y is less than or equal to y. Okay. In other words, what is y? Big Y. What is big Y? Big Y is nothing but ax plus b, this. So this is the probability that ax plus b is less than or equal to small y. But this is in terms of x, so we can compute this. Okay? So simply do an algebraic manipulation inside this, to not change the inequality. Okay, this, ax plus b is less than or equal to y if and only if x is less than or equal to y minus b over a if a is positive, right? If a is positive, this is equivalent to this. But if a is negative, the inequality switches direction, right? So x is bigger than or equal to y minus b over a. Okay, is everybody following? Let me ask you. So what do we do when a is 0? Maybe, yeah. What do we do when a is 0? Huh? Good. A is not 0 as given in the problem, because then we would have a problem. What would break down if a was 0? Huh?
And y become constant?
Exactly. Y would become exactly equal to b. And in that case, there is no PDF. Okay. So now I know that most people are following. Very nice. So let's write this in terms of the CDF of x. This is fx of y minus b over a. Whenever a is positive, and when a is negative, I can also write this in terms of fx. I can write this as 1 minus fx of y minus b over a, right? Again, I'm using the fact that x is continuous. Otherwise, I would have to add to this the probability that x is exactly equal to y minus b over a. But I don't need it in this case, because x is specified to be continuous, and the probability of x taking any certain value, any scalar value, is 0. Okay. What's next in the procedure? Remember, step number 1 was write down the CDF of y. Step number 2, evaluate it in terms of the CDF of x. Step number 3 is, if y is continuous, differentiate to get the PDF of y. Well, can I differentiate this? Is this differentiable? Yes, because I know x is continuous, so this must be differentiable, and this must be differentiable as well. So I'm going to differentiate. So fy of y is d by dy big F, which is, well, differentiating this gives me 1 over a fx, oops, sorry, fx y minus b over a. And differentiating this gives me negative 1 over a fx y minus b over a. And that's valid for negative a. Okay? So I can combine these two by using the absolute value sign as a compact expression, valid for all scalar a except 0, of course. So there you go. Now, do you see why this scaling with a is coming? Okay. So it's related to the derivative of the function linking x and y. Okay. So I would like you to think about it. In fact, I would like you to worry about the general case. So think about the general case, y equals g of x. Okay. And g is not necessarily a linear or an affine transformation. Okay. But I would like you to get an expression for fy in terms of fx. The expression will involve the derivative of the function g. Okay. Consider the case where g is monotone, meaning it is either monotone decreasing or monotone increasing. Okay? So think about this as an exercise, and we'll address this next time. So let's move on. Here's another exercise. So these are 2 exercises for you. Let's say exercise. Number 1 is this. Number 2 is written in the notes. Show that a linear function of a normal random variable is normal, meaning x is Gaussian with mean, let's say mu, and variance sigma squared. Okay, and y is ax plus b. Using just simply with an application of this, which we proved, show that y is also Gaussian with mean A times mu plus B. And what is the variance? Very nice. A squared sigma squared. Now that we've proved this, we are in a position to show that when you linearly scale a Gaussian, you get another Gaussian. Remember, earlier I just told you this without showing you. Now you're in a position to show this. Okay, very nice. Any questions? Okay. Any questions or comments about this? Okay, the next topic is functions involving more than one random variable. Okay. Here we cannot really apply apply shorthand techniques, but the general procedure continues to be useful, of course, because general procedure is using the basic definitions. Okay, so I said this lecture is all about examples. I'll go through this topic again with examples. So here is the example that we'll do first. X and Y are both uniformly distributed in 0 to 1. Okay? And they are independent. Z is obtained by multiplying X and Y. Find the PDF of Z. Excuse me? It's very nice that you actually, that's a good question, because it's a common misconception, as I have heard from the instructors of EE 306, that in this situation many students simply multiply fx and fy. Okay. But multiplication of fx and fy gives us the PDF of, well, gives us their joint PDF in this case because they're independent. What is z, on the other hand, z is the product of x and y. Okay? So, x and y are independent. This implies that fxy of x comma y, it's the joint density of with two independent variables. This is the product of the marginal densities, and this is true. However, z equals x times y has nothing to do with this xy that we write here. This xy that we write here is just a notation that that simply means this is the joint PDF of x and y. Okay? So I think this is a good example for illustrating this common misconception and preventing this, misunderstanding to continue. So, how do we find the PDF of z? Or how do we find, for example, the probability that x times y is less than or equal to z? That would be fz of z. Well, we would integrate over the region of xy pairs such that x times y is less than or equal to z of the joint density xy dx dy. I would like you to really look at this, and I don't want to move on until everybody is okay with this expression, or everybody's comfortable with this. So do you see, you're right, do you see now? So what are we computing here? We are integrating the joint density of x and y over the region where their product is less than a certain value, which is z. Okay? That gives us the probability that x times y takes values less than that particular value z. Okay? So, let's get into the specifics of this problem, where x and y are, for simplicity, we're working with the uniform distribution again. X is uniform from 0 to 1, while y is again uniform from 0 to 1. So their values live in this square. While in the square, so this is x, this is y. Doing this integral means integrating over what region? Integrating over the region where x is between 0 and 1, y is between 0 and 1, and their product is less than or equal to z. xy equals z gives us such a curve, right? And for a particular positive value of z between 0 and 1, so this is the xy equals z curve. And it's going to intersect with the square provided z is between 0 and 1, right? So, fz of z, which is the probability that x times y is less than or equal to z, is nothing but the integral over this region. Let's call it region AZ. Integral over AZ, fxy, xy, dx, dy. Okay, this is the point at which we can benefit from independence. Why? Because this fxy, the joint PDF, will break into the multiplication of fx and fy. Right? And fx of x is nothing but 1 when x is between 0 and 1, and fy is nothing but 1 again when y is between 0 and 1. So this is very easy. It's not going to cause any problems. All we need to do is get the limits of integration right. Okay? So let's examine this region. In this region, as x goes from 0 to this point, we're integrating over y from 0 to 1. So we have this rectangle, we have a small rectangle. Well, what is this point? What is this value of x where the curve intersects z? It's z, yes, or z over 1. Okay, so up to z, let me write down this integral. As x goes from 0 to z, y goes from 0 to 1, and the joint density is nothing but 1 times 1 dx dy. Right? The joint density, well, fx of x is 1, fy of y is 1, as long as x and y are between 0 and 1. I want to just write the integral. Of course we can compute. Yes.
Değişimini sıfırdan z over y'ya hani y ile sıfırdan böyle alıp bu şekilde öyle yazamaz mıyız?
We can write this in many ways. But I want to, well, x goes from 0 to z. Of course, you can start from y, or you can just write down the fact that this area is simply equal to z. Yes. We continue as x goes from z to 1. This time, when x is in this region, y goes from 0 up to z, right? No, 0 up to z over x. Y goes from 0 to z over x. Again, the integrand is very easy. Okay, so by inspection, the first part of the integral is trivially equal to z. The second integral, it's computed. It's z to 1. This is z over x dx. Maybe I should have said dy dx. Let's change the order, because the inner integral is in terms of y, the outer integral is in terms of x. Right, which is z plus z ln x as x goes from 1 to z, so z ln 1 minus ln z, which gives us z minus z ln z. Any questions? Yes, please. Because they are both uniform between 0 and 1. So if you look at fx of x, it's this. Similarly, fy of y is this. We multiplied fx and fy, and we are integrating over this region. But we broke this region into these two parts. This first part, which is the rectangle, and the second part. Because the nature of the limits of the integration change from this part to this part. In this part, we just have x goes from 0 to z, y goes from 0 to 1. In this part, it's different. The y goes from, basically, we have two curves limiting our region from the above. That's the reason for the two pieces in the integration. So from above, we are limited by y equals 1 and x times y equals z, two curves. From the right, we are limited by the curve x equals 1. From below, we are limited by y equals 0. From the left, we're limited by x equals 0. Okay, so altogether, there are 5 curves. And the region is formed by these 5 curves. Okay, so anyway, this is our CDF. What is the final step? Differentiate. So let's find fy of y as d by dz, the CDF, I'm sorry, fz of z. Fz of z. What is z? Let's remind ourselves, z is x times y. Fz of z is the derivative of this, which is 1 minus ln z minus z times 1 over z. And what do we get? We simply get negative ln z. It's a funny looking density function. What do you think? Is that negative? No, because of the region of z that we're talking about. Remember, throughout all this, we are limited to z between 0 and 1. Why? For other values of z, the curves don't intersect. And the region has no area. Okay? So this density is valid for z between 0 and 1, and it's 0 otherwise. Okay? By the way, let's see, we can make a sanity check to see if our cumulative distribution function, big Fz of z, satisfies some of the properties that a CDF should satisfy. First of all, does it start at 0? Now, this is, if you write the limits, this is equal to this expression if z is between 0 and 1 and it's 0 otherwise. Let's try plugging in z equals 0. When you plug in z equals 0, we get 0 minus z ln z at 0, which is 0. So that's good. Fz of 0 is 0, so our CDF really does start at 0. Does our CDF go to 1 as z goes to infinity? We don't have to try z equals infinity. We just need to plug in z equals 1. 1 minus 1 ln 1 is really 1. So that's good. This sort of assures us that this CDF makes sense. Let's also see if this density makes sense. If we try to plot it, Fz of z between 0 and 1, at 0, it's going to blow up. Okay, it's going to be arbitrarily large at 0, and at 1, it goes to 0. Okay, this is our PDF. Now let's see what this implies. Where did we come to this from? All we did was to take two uniform random variables that are uniform between 0 and 1 and multiply them. When we multiplied them, since they are both less than 1, they tend to make each other smaller. And their product is more likely to be close to 0 than closer to 1. Which is, when you look at this, it's supported by this PDF curve. What is maybe more interesting is that the PDF goes to infinity at 0. It blows up at 0. That's actually a deep point that could result in interesting phenomena. Any questions about this? In that case, when we came to this point, we would have to substitute in the joint PDF. We couldn't simply write the joint PDF as the product of the individual marginal PDFs. That would be the only difference. So if someone tells you that the random variables are dependent, they have to specify for you the dependency. And one way of the most certain way of specifying that dependency is to give you the joint density function or the joint cumulative distribution function. Any others? Yes, please.
Yani şimdi 1'de 0 oldu, 0 oldu, sonsuz oldu. Yani 1 olma ihtimali var ama aslında. Mesela kesin
Right. This is not a probability. Remember, this is a density function. we find probabilities by integrating the density function. So, for example, you can find the probability that it lives between 1 minus epsilon to 1 by integrating this very small, integrating this tail over this region. And yes, that would give you a very small probability. So it just says, this is interesting, isn't it? It's quite interesting. It's deeply related to real numbers. Okay. When you just basically they are both less than 1. So when you multiply the product, it's clearly more likely to be to the left of 1/2 than to the right of 1/2. But the fact that it's so steeply inclined to this region is interesting. Yes. I think this is also kind of, I find this kind of connected with the following example, which is sometimes known as the two-envelope paradox. Okay, so here's the setup. Somebody gives you 2 envelopes. Okay, one of them has a positive amount of money in it. Let's say X. The other has twice that much. Okay, 2X. So when I give you an envelope, should you keep that envelope or should you switch to the other one? Now, if you view this from a point of view of expectations, you will find that the expected value of the money you make by switching is always larger, which seems paradoxical. Okay? Think about this problem. Okay, this is because x is a real number between 0 and infinity, and 2x is a real number between 0 and infinity. Okay? Now, it doesn't seem to make sense, but think about it. Also, you may say, what may be the best strategy in such a game? Always switch doesn't seem to be a clever strategy because of symmetry. Of course, a better strategy would be look at the amount of money you have in the envelope and decide according to the value of the money in the envelope to whether to switch or keep this money. Okay? So, time is up for today. We'll continue from here next time.